In this video, we're going to explore the concept of absolute dating further, specifically through the example of one radioactive isotope, which is carbon-14. Now, carbon-14 is a really important radioactive isotope for determining ages of different samples that live throughout Earth's history. And specifically, carbon-14 is found frequently within plants and animals. For this reason, it is used to date samples of biological origin, such as bones and fossils, that formed relatively recently. So in the last video, we referenced crime shows where we can find a body and figure out exactly how long that body has been dead for. And that is done through specifically carbon-14 dating techniques, because again, living organisms, specifically plants and animals, contain carbon-14 already. Now, carbon-14 has a relatively short half-life of 5,700 years. I know that doesn't seem really short to you guys, but in terms of Earth history, 5,700 years is not a really long period of time. And since it has a short half-life, it can only be used to determine the age of samples that are up to 50,000 years old. Anything older than 50,000 years old, carbon-14 can be used to determine the life of. And the reason for that is, over time, there would not be enough carbon-14 left to determine the age of a sample greater than 50,000 years old. So if you look here at the diagram that's found on the front cover of your reference table, remember that we have our radioactive isotope carbon-14. And because its half-life is 5.7 times 10 to the third power, or 5,700 years, it can only be used to date organic samples less than 50,000 years old. But that's also really helpful because we do have a lot of fossils in Earth history that do meet that criteria of less than 50,000 years old, so it is very useful. The other three radioactive isotopes on our reference table, you can tell, have much larger half-lives. They are in the billions to years old in terms of half-lives, and these are used to date geologic samples that are millions to billions of years old, such as rocks, for example. This is how we know that the age of the Earth is 4.6 billion years old, because we found samples of meteorites that have radioactive isotopes, and we were able to use those isotopes specifically to figure out how old those samples are. So what we're going to do today is go through some example questions of radioactive dating. The question that we're going to look at first is, a fossil formed 11,400 years ago. Which percentage of the original amount of carbon-14 remains in the fossil? So we know that the age of the fossil is 11,400 years old. We're given that information, but we need to figure out how much carbon-14 is within a fossil that has that age of 11,400 years ago. To do this, I'm going to introduce you guys to a model of radioactive decay that I've created. Blank copies of this model have been provided to you as a resource on Google Classroom. You can feel free to print these out as many as you need, and you always have a model to use when doing these types of word problems. I'm also going to show you in a different video how you can do this model of radioactive decay through the drawing feature on Google Documents. But for right now, I'm going to show you an example of how to use this model to answer a question like the one we have here. First thing we need to remember is our information about our radioactive isotopes. This question is about carbon-14, so we're only going to focus on that isotope. Something that we need to know is the disintegration product. When carbon-14 breaks down and decays over time, carbon-14 always turns into nitrogen-14. We call that our disintegration product. We also need to remember the half-life of carbon-14, which is 5,700 years. So now let's figure out how to fill out this model. The first thing we're going to fill in is the name of the radioactive isotope that we're using in this question, and that is carbon-14. The disintegration product, which can be taken from the front cover of the reference table, we know is nitrogen-14. Now for starting value. This is going to be important depending on the type of question I'm asking, In this case, we're dealing with percentages. So our starting value, anytime you're dealing with a question that has percentages, is going to be 100%. So let's figure out how to use this model. Initially, before any time passes, we're going to assume that our organic samples always have 100% carbon-14. But as time goes on, let's say as 5,700 years passes by, after one half-life, 5,700 years, well, we know that after 5,700 years, carbon-14 gets cut in half. So that 100% of carbon-14 turns into 50% carbon-14. Now, the other 50% just didn't disappear. That other 50% turns into the decay product, which is nitrogen-14. So now we have 50% carbon-14, 50% nitrogen-14. So now, if we were to find a sample that has 50% carbon-14 and 50% nitrogen-14, that tells scientists a lot of information. That tells scientists that the age of the sample is 5,700 years old. Because in order to get 50% carbon-14, that means one half-life must have passed by, 5,700 years must have passed by. So if we get this 50% carbon-14, we know that the age of the sample is going to be 5,700 years. So now let's keep going in this chart. More time passes by, another 5,700 years goes by. That means we've experienced 2 half-lives. Now, that 50% carbon-14 that we have after 5,700 years gets cut in half again, so that 50% carbon-14 turns into 25% carbon-14. Because remember, the half-life is always the amount of time it takes for a sample to be reduced by half. So from 50% carbon-14, we're going to 25% carbon-14. That means the remaining part of the sample is 75% nitrogen-14. So now at this point, we need to figure out what is the age of the sample. If we find an organic sample with 25% carbon-14, we're going to be able to figure out the age because since the beginning, we had 5,700 years go by plus another 5,700 years go by just to get to this point. If you add 5,700 and 5,700 together, we get the age of the sample, which is 11,400 years old. Now, if you remember the question, you'll notice that we've actually answered it at this point. A fossil that's 11,400 years old is going to have 25% carbon-14 within it. So we just answered the question, but we're not done with the model yet. So I want to show you how to fill out the rest of the model just in case it's useful for questions in the future. So now that we have 25% carbon-14 and another 5,700 years goes by, that 25% carbon-14 is going to be cut in half to 12.5% carbon-14, and the remaining sample is going to have 87.5% nitrogen-14. At this point, if we want to find the age of a sample that has 12.5% carbon-14, we have to add up all of the time that has passed since the beginning. So 5,700 plus 5,700 plus another 5,700 gets us to 17,100 years. So this is an example of how to use this model of radioactive decay for carbon-14 when you're dealing with questions regarding the percent remaining. So now I just want to show you this in a very different way, just as a graphical analysis of radioactive decay of carbon-14. So in this question, on the x-axis we have time, but it's represented in terms of half-life, so the number of half-lives that's happened. And then on the y-axis we have the percent of original mass of our substances. So to start, we need to recognize that there are 2 curves on this graph. First curve is the disintegration product. The second curve is the curve for carbon-14. So here we have how much carbon-14 is in the sample, and then also how much of the disintegration product is within the sample. And in this case, it would be nitrogen-14, because carbon-14 always decays into nitrogen-14. So when we are at time 0, when no time has passed at all, we can see that our disintegration product is at 0%, and our carbon-14 amount is at 100%. But now, after one half-life goes by, look at what happens. We have 50% of both carbon-14 and nitrogen-14. After another half-life goes by, that carbon-14 is cut in half again, so that turns into 25% carbon-14, and now we have 75% of nitrogen-14. So this is just another way of getting the same information off of a graph. So I want to end today showing you one more example question that is slightly different from what we saw before. The question is, how much of a 400-gram sample of carbon-14 will remain after 17,100 years of radioactive decay? What's different about this question is now we're dealing with a mass instead of a percent. Instead of saying we have 100% carbon-14 initially, we are told that the sample has 400 grams of carbon-14. And after 17,100 years, how many grams will be remaining? Luckily, we can still use this model to help us figure out questions in regard to mass. So we still know that a radioactive isotope is carbon-14. Carbon-14 always decays into nitrogen-14. But now our starting value is going to be different. Instead of starting with 100%, we're going to be starting with 400 grams. So in our first box here, I'm going to start with 400 grams of carbon-14. After 5,700 years goes by, that 400 gram of carbon-14 gets cut in half. So we get 200 grams of carbon-14, which means 200 grams of nitrogen-14. And at this point, the age of our sample is going to be 5,700 years. Another 5,700 years goes by for a second half-life. Our carbon-14 is going to get cut in half again, but this time our 200 grams of carbon-14 is going to get cut in half to 100 grams of carbon-14. This means we're going to have 300 grams of nitrogen-14. Now, at this point, after 2 half-lives, if we have 100 grams of carbon-14 remaining, this means we had 11,400 years pass by. Now, more time goes on, another 5,700 years passes. Our 100 grams of carbon-14 is going to get cut in half again to 50 grams of carbon-14, which means we have 350 grams of nitrogen-14. If we're going to add up all the time that has passed at this point, 5,700 plus 5,700 plus 5,700, the age of our sample is going to be 17,100 years old. And if we go back to the question, we have our magic number. How much will remain after 17,100 years? Well, at this point, we are left with 50 grams of carbon-14.